ahí se dispara una serie de asuntos generales acerca de la modalidad en la teoría física. Entonces nosotros obtendríamos nuestro análisis de la modalidad física a partir de estas colecciones de modelos. Ahora, antes que la publicación de Sam, estaba el trabajo de Catherine Brading sobre modalidad. Ella lo desarrolla dentro del marco del realismo estructural, que yo creo que es dispensable. Ella dice que los theoretical kinds of objects de una teoría de alto nivel están exhibidos, presentados, exhibited, en la estructura compartida de los modelos de la teoría. Aquello acerca de lo cual habla una teoría es, en primer lugar, ¿no es cierto?, no los objetos físicos particulares, sino que estos theoretical kinds of objects. Entonces, de nuevo, acá nosotros tenemos objetos particulares, uno podría decir en la jerga metafísica instanciados, y después objetos que son kinds, que son posibles. Entonces también apuntaría en una dirección que yo encuentro sumamente interesante. Y después dice, our commitment to a theory is equivalent to our placing a restriction on our beliefs about what will and will not happen based on what theoretically can, cannot, and must happen. Entonces ya lo que sostiene es que the main import of the modal features of our theory deriva de esto, ¿no? O sea, de lo que las teorías, en este caso la estructura compartida de los modelos, sugieren acerca de kinds of objects, no actual objects, sino que kinds of objects. Y esa modalidad sería aquella que guiaría nuestras acciones y sería suficiente para sostener el discurso modal en un nivel teórico, pero acá hay un punto clave, without making any commitment to modality at the ontological level. Entonces ahí a mí no me queda claro lo que quiere hacer Catherine Brading, si acaso ella realmente se quiere comprometer ontológicamente con la modalidad, que es algo que yo quiero hacer, o si en cambio ella, por dejar a un lado el discurso metafísico, estaría simplemente reduciendo la modalidad a aquello que theoretically, ¿no es cierto?, teóricamente nos dicen nuestros modelos. Eso a mí no me queda muy claro. Después Gina Ismael es más franca al respecto, ¿no es cierto?, cuando delinea su concepción de modalidad para los empiristas, dice que yo defiendo una teoría empirista de la modalidad, que fíjense por favor en esto, dice that keeps a substantive account of modal commitment, but throws out the metaphysics. Con eso yo estoy de acuerdo, hay que dejar a un lado la metafísica, yo me quiero deshacer de esa oposición entre ecumenismo y metafísica. Pero ella dice, yo sugiero que si colocamos a la par, si unimos una actitud deflacionaria hacia la representación con una actitud sustantiva acerca de cómo funcionan los modelos, cómo son construidos y puestos a trabajar, el resultado es una teoría que deflaciona, minimiza la metafísica del compromiso modal, sin deflacionar el contenido modal de los claims, ¿no es cierto?, de los modal claims. Entonces acá la postura de Chinon Ismael es claramente epistémica. Dice que el contenido modal de nuestros modelos tiene que ser entendido en términos de los roles que ellos juegan al guiar nuestra predicción y las decisiones. Ahora, hay un draft bien interesante, todavía no publicado, de John Norton, que también es acerca de modalidad para los empiristas. Y lo que Norton dice es que es algo que es bien intuitivo, pero yo encuentro que es re interesante. Dice, what's possible according to the empiricist conception is what our evidence positively allows. Entonces esa sería la posibilidad física. Lo que la evidencia inductiva, ¿ya? Lo que la evidencia inductiva permite. En cambio, lo que es necesario es aquello que la evidencia obtenida, ¿no es cierto?, por medio de observación, experimentación, detección, medición, inductivamente, en este caso, nos compele a inferir. Entonces ahí hay definiciones empiristas ¿no es cierto?, de posibilidad y de necesidad. Y después esto, bueno, la verdad es que me encanta, pero ya está en harta gente antes, ya está en Jack Smart, por ejemplo, el filósofo australiano-inglés, en papers de 1960, 1970, dice, yo no le otorgo a las leyes científicas ningún estatus cualitativamente especial en comparación con otros hechos contingentes. Esto es clave y es algo que comparte la literatura que busca ofrecer concepciones físicas acerca de la modalidad, porque la distinción que se compró por mucho tiempo, ¿no?, en el debate acerca de fenómenos que son necesarios, fenómenos que son contingentes, acá se diluye, ya no está esa distinción. Entonces las leyes no tendrían ningún estatus especial, ellas no serían algún tipo de verdad de orden superior, más allá de las verdades contingentes ordinarias, no tendrían un alcance superior, no tendrían aplicación universal. Ahora, los empirical requirements de Norton son bien interesantes. Por ejemplo, la posibilidad empírica estaría determinada por apoyo inductivo, evidencial. Entonces, este apoyo inductivo tendría grados. La necesidad empírica también tendría cierta compulsión evidencial, ¿no es cierto? Cierta fuerza evidencial. Pero sería cierta fuerza que solamente se mide en términos de este threshold. Hay una cierta barrera que nosotros acordamos para juzgar que algo es necesario. Y el caso de la necesidad lógica sería un caso límite, que solamente se obtiene cuando la evidencia deductivamente entraña, ¿no es cierto?, una posibilidad, una actualidad, etcétera, pero en términos siempre de evidencia inductiva. Después está el requerimiento de la actualidad evidencial, esto de la realidad evidencial, podríamos decir en español, los cuerpos de evidencia empleados tienen que reportar, basarse en reportes de experiencias reales. Entonces acá hay una conclusión muy humilde, ¿no? No, pero que no creo que esté tan flaca. Es una conclusión muy humilde que dice que podemos tener, ¿no es cierto?, modalidad física para las leyes físicas. La modalidad nómica sería, vale la pena decirlo, modalidad física. ¿Eso qué quiere decir? En contra de las concepciones metafísicas, no tenemos que añadir, postular capas ontológicas adicionales para obtener la modalidad, ni tenemos que obtenerla de fuentes extracientíficas. Y también, contrario a las concepciones humeanas, no podemos deshacernos de la modalidad física, como lo creería, ¿no es cierto?, el defensor del mosaico humeano, o de la teoría de la regularidad, porque el mundo físico es modal, ¿no? Esta taza es modal, las cosas físicas alrededor son modales, etcétera, pero son físicamente modales. Y después, bueno, la posibilidad física y la necesidad física vienen en grados. Los fenómenos no se dividen en necesarios y contingentes as a matter of kind. No es que hayan kinds of objects, como por ejemplo Mark Lynch lo querría. Y habría una tesis de la continuidad. Hay grados all the way up and down. ¿No es cierto? Hay grados de posibilidad, grados de contingencia que se juzgan en base a nuestros mejores modelos y teorías, o conjuntos de modelos que permiten las teorías. Y después tendríamos modalidad nómica que estaría incorporada, ¿no es cierto?, en las redes teóricas. Los modelos y las teorías nos informarían acerca de la posibilidad física. En este sentido, a mí me interesaría explotar, ¿no es cierto?, en más detalle, ciertas características compartidas que se encuentran en estas propuestas que antes yo mencionaba. Y también me gustaría sostener, desde una perspectiva experimental, que podemos acceder a la modalidad nómica a través de diversos medios experimentales. Y esto es re interesante porque nuestro acceso a la modalidad no sería una cuestión de todo o nada, porque por supuesto hay grados, entonces nuestro acceso podría fallar. El mundo podría decirnos que las cosas son de otra manera, que nos equivocamos en nuestra predicción de posibilidades, que nos equivocamos en nuestro juicio de necesidades, o que otras necesidades están ahí presentes, etc. Entonces, esta es en verdad la tesis de esa sección del capítulo del libro, que espero poder convertir después en un paper. Y habrían dos objeciones. Por ejemplo, acá yo me imagino a alguien como Stephen French, que de hecho me ha dicho esto. Él me colocaría esta concepción ante este dilema. Él diría, bueno, your view ends up collapsing with humanism. ¿No es cierto? Eso es lo que él siempre sostiene. Si tú quieres situar la modalidad, la teoría y los modelos, entonces tú eres un humeano. Eso es lo que haría David Lewis, según él. Y yo le diría no, porque el humeano parte de este mosaico amodal, de particular matters of local facts, ¿no es cierto?, que son amodales. En cambio, yo partiría de un mundo físico que es modal, ya que es físicamente modal. Y él después diría, bueno, entonces si no eres humeano, tienes que aclarar, ¿no es cierto?, tus compromisos metafísicos, porque algún presupuesto metafísico hay. O eres un disposicionalista, un estructuralista, un primitivista, etc. Y ahí de nuevo yo diría, no, porque esas ontologías son added layers, ¿no es cierto?, de ontología. Y después
Ese minuto, Cristian, perdón.
Ok, gracias. Sí, estoy terminando con esto. Entonces, una segunda objeción sería esta preocupación que emerge de la filosofía de las matemáticas aplicadas, en particular, ¿no es cierto?, del artículo de Eugen Wigner de 1960 en adelante, que a la fecha Aresu Islami, la San Francisco State, ha explotado muy bien, que podría sostener que al menos parte de la modalidad de las leyes físicas es modalidad matemática. Y de hecho uno podría sostener ahí que efectivamente la preeminencia, ¿no?, de las ecuaciones diferenciales en la formulación de leyes, sobre todo la aparición de surplus mathematical structure, podría inclinarnos a creer que hay modalidad matemática en la ley de física, y que esa modalidad matemática es, por supuesto, matemática y no física. Sin embargo, la respuesta ahí tendría que sostener que esa modalidad sería físicamente relevante solamente en que las matemáticas estén físicamente interpretadas. Pero eso es un punto que todavía yo no he podido desarrollar. Bueno, quedo acá. Parece que planifiqué bien la presentación.
Gracias,
Sí.
Cristian. Tenemos
Sí,
algo
no
así
sé
como
qué,
9 minutos para preguntas.
sí,
Si
no sé
pueden
qué les
levantar la
parece.
mano o escribir en el chat que piden la palabra. Sorry, you can raise questions now. You can either raise your hand or write down in the chat that you want to ask a question. We have around 8-9 minutes for that. Franco, por favor.
Sí, muchas gracias por la presentación, Cristian. Muy interesante, como siempre. Un tema que hemos conversado harto igual. Y ahora me quedo con la duda en esta presentación. O sea, me surge la siguiente duda. Si la modalidad es algo que proviene de nuestros modelos y nuestras teorías, claro, se cae en este peligro de interpretar que, entre comillas, la modalidad a la que nos estamos refiriendo es la modalidad finalmente matemática. Y no me queda tan claro cómo se puede distinguir esa modalidad matemática de nuestras teorías, de nuestro modelo, de una modalidad física supuestamente instanciada sin acudir a supuestos metafísicos. No sé si podría
Claro,
aclararse.
claro, sí. Súper buena pregunta. Es una pregunta difícil. Igual, no tengo como una respuesta sumamente clara. Por supuesto, es una pregunta difícil. Lo que yo creería, claro, es que si hay, por ejemplo, surplus mathematical structure en una teoría física, entonces uno tendría que ver qué roles juegan, ¿no? Puede ser que jueguen roles simplemente inferenciales, roles inferenciales que no tienen ninguna pretensión de informar físicamente acerca de nada. Yo siempre estoy molestando por teléfono a Pablo con la cuestión de la introducción de los irracionales, ¿no?, en la ecuación de Schrödinger. Y después uno podría decir, bueno, hay otras matemáticas que en verdad no son tan surplus, que no juegan solamente roles inferenciales, sino que son más bien físicamente informativas. Eh, pero sí, no, la pregunta es difícil, Franco. La verdad es que no tengo una respuesta muy definitiva. Sí, sí, gracias, Franco.
Gracias, Franco. Sam, go ahead, please.
Thanks very much, Christian. I had a question about, on your view, whether or not different types of theories, or the modality that we get, the physical modality that we get for different types of theories should be interpreted differently. So there are some physical theories that are intended to be instrumental. So for instance, theories like in modern cosmology that use very explicitly idealized models. So the standard Friedman, Lemaitre, Robertson, Walker models, for example, have a very simplified representation of our universe, and the different possibilities that are described by the different versions of these models describe or represent certain features, but there are certain things that it seems like they represent that we know are not true. So for instance, they represent all of the matter as being homogeneously distributed. And fortunately for you and I and the rest of us, it's not homogeneously distributed, because otherwise we wouldn't be here. Nonetheless, we still think that somehow the models of cosmology represent physical possibilities, but they can't be in the way that, for example, Norton says, because we already know that the possibility that it represents is too simple to represent our actual world. I was hoping you could say a little bit more on how, on your view, we should understand these sorts of possibilities that our physical theories describe.
Yeah. Well, I can't say much about the case study you mentioned because I don't know that, that situation. But I think that one of the morals that I drew from your recent contributions on physical modality has to do with the fact that modality works differently in different theories. You actually go through cases of classical mechanics and thermodynamics and so forth, and then, well, it seems natural to think that the modality about which we talk in each of these theories works differently, is different in character. Now, in favor of Norton, he actually mentions in this draft that there are some cases in cosmology in which we talk about modal claims in cosmology about which we don't have any direct on any potentially actualizable evidence. And he mentions a few cases there. But he tries to put the situation down saying the following, that we in any case should have any background information, any background physical information in order to derive inferences that are physically informative about our models. And yeah, what I will try to do there, but that's far ahead from what I'm doing now, is to go for local conceptions of modality, local understandings of modality in different models, different levels of abstraction and idealization, different levels of requirement of the threshold for evidence, and so forth. Maybe that's one of the confusions that arises from the predominance of humanism and metaphysics, that we are all the time attempting to constitute, to provide a global understanding of modality, when things are actually local in each case. But yeah, I don't have much to say about the case study. Yeah, thank you.
Más preguntas? Any further questions? Cristian, muy corto, Cristian, tenemos 1 minuto 15 segundos.
Cortito, entonces, no, una duda que me quedó, no sé si entendí mal, es si hay si la respuesta que tú le das a Stephen French, en el fondo, trades en una ambigüedad de ¿qué es la physical modality que tú estás defendiendo ahí? ¿Es la modalidad que aparece en la ciencia física o es la modalidad que observamos en los objetos físicos como tu taza?
Ok, sí, ya está. No, está complicado. Yo creería que en la ciencia física, pero nosotros asumimos que, bueno, nuestras teorías y modelos físicos son la mejor fuente de información que tenemos acerca de la naturaleza física, ¿no? En ciertos dominios. Ahora, el punto acá, lo que yo les decía de lo de Stephen French, es que alguien como él diría, bueno, pero your view ends up collapsing with humanism, porque estás reduciendo la modalidad a las teorías, a los modelos. Entonces eso es lo que hace el best system account. Y uno podría decir, no, porque el humanismo parte de una ontología amodal, de este amodal stuff. Y entonces ahí él diría, ok, pero si tú crees que hay modalidad en el mundo, entonces tienes que to come clear, ¿no es cierto?, acerca de las metaphysical presuppositions. Y él diría, por ejemplo, yo soy un estructuralista realista. Creo que está esta fundamental structure of reality. Y ahí yo le diría, bueno, no, porque esa postulación es demasiado metafísica, es demasiado heavy, es muy exclusiva para la física fundamental. Entonces ahí uno apuntaría en esta dirección de, ¿no es cierto?, leer la modalidad física, obtenerla a partir de los modelos y de las teorías, pero localmente. O sea, puede ser que, ¿no es cierto?, en fundamental physics el estructuralismo funcione bien en algunas áreas, pero puede ser, ¿no es cierto?, que en otras áreas como la cosmología no, o en usos de la mecánica clásica no, o en usos de la biología no, etc. Claro, sí. Sí. Es complicado, en verdad, no, ahí falta quizás un poquito más de trabajo.
Gracias, Cristian. la Roulette y Soto, especialmente Soto por la presentación. Perdón Álvaro, pero tenemos que continuar. Propongo que si queda tiempo y si los expositores tienen un ratito al final y quedan preguntas pendientes lo pueden hacer, pero si alargamos la cosa ahora, le podemos generar problemas a la agenda del día, al resto de la gente. Así que quizás podemos ver ahí.
Gracias. Muchas gracias a todos.
So I'll go in English now. Our next two speakers will present in English, so I think it's better if we go along in English. So now it's Sam Fletcher's turn to present. So I'm sorry, I don't remember the title of your talk. I have to open it here, but feel free.
Surplus structure arguments. Should I share my screen?
Yes, please. You're able to do it, are you?
I think so. How does that look?
Yeah, great.
Great.
Shall I give you a warning or something of around 15 minutes or something? You tell me.
That would be great. Thank you.
Okay.
Thanks for the invitation, folks. I am sorry that we can't all be together in Chile and have a nice ceviche and look over the ocean together. I would have liked that, and I hope we'll be able to do that in the future. The topic of my discussion today is surplus structure arguments. So the prototype for this sort of argument is the classic discussion that we have between Leibniz and Clarke regarding the reality of space. So you'll remember from the history of philosophy that Leibniz proposed different sorts of arguments to try to show that in modern terms, space or a commitment to absolute space was something that we could do away with, something that we could dispense with. And he came up with different arguments for this that involved symmetry properties of space and time. Some of these involved static shifts, that is either in space or in time, where we shift all of the things in space over, say, by 1 meter to one side, or we shift them in time 1 second earlier or later. He observed that it would make no difference to any of the goings on in the world to make this sort of shift. And so the differences between the two, using his principle of the identity of indiscernibles, would then entail that the situations described were the same. And one could give an analogous argument for kinematic shifts, where one, instead of translating all of the objects from one spatial location to another uniformly, gives everything a uniform velocity in a particular direction. Even though the resulting world would have different speeds and absolute speeds and velocities for different objects, the observable features of the world would stay the same. Now, of course, Leibniz's principle of the identity of indiscernibles and his principle of sufficient reason, which he used in these contexts, are controversial. But nonetheless, many think that there is some key underlying insight that doesn't depend on special philosophical principles like that, but that is a more pervasive and central feature to how we reason with symmetries in physics. So one of the challenges to understanding this, however, is what exactly the form of the argument is supposed to be in general. Gordon Bellett, in a nice review article from about 8 years ago now, said that these sorts of arguments, which I'll be calling surplus structure arguments, seem like they commit to the following two principles. So one, which he labels D1, is that the symmetries of a classical theory just are the transformations that map solutions of the theory's equations of motion to solutions of the theory's equation of motion. That is to say, the symmetries are the objects that map physical possibilities to physical possibilities. Second, and this is intended to be a kind of definition, or at least a naive definition of symmetry. And then the principle that he thinks is used in the argument, or the one that seems most obviously used, which he labels D2, is that two solutions of a classical theory's equation of motion, so two physical possibilities, are related by a symmetry if and only if they are physically equivalent. We saw that the statically shifted goings on in Newtonian space-time were like this. Similarly, with the kinematically shifted goings on. The argument is supposed to be that because those shifted goings on described by some model or other are related by symmetries, that they in fact represent the same states of affairs, they're physically equivalent. However, Bellet shows, and it's just a couple of lines of argument thinking about the underlying logical structure of these two principles, that this entails that all solutions are physically equivalent when we combine these two. That's obviously an unwelcome conclusion because we do think that different solutions, different physical possibilities can represent indeed different states of affairs. So he says, I leave it as a challenge to the reader to identify a general and interesting formal notion of symmetry, that is a rendering of D1 that renders D2 true. So Bellet thinks that he understands the relevant notion, the relevant principle that's used in the surplus structure argument, but that the naive definition of a symmetry is the problem. So my goals today are to actually reject both of Bellet's D1 and D2. I'm going to reject his definition of symmetry for a more formal definition of symmetry. And I'm going to expound a form of the surplus structure argument that makes use of this notion of symmetry, but that describes the surplus structure argument, or the form of the argument, as having a rather different form than Bellet imagines, in particular one that doesn't use his principle D2. Okay, so first I'm going to have an introduction to the notion of symmetry that I'm using. Then I'm going to apply that notion of symmetry to the surplus structure argument. I'll address one objection that has arisen in the literature to this sort of strategy that I'm using. And then I will go back to Bellet's formulation and recapitulate my conclusions. So let's start with the notion of symmetry that I would like to use. So I'm imagining a situation where we have some physical theory. That physical theory provides us with a space of models of some physical system of interest. So for instance, cosmological models in cosmology, the models of quantum mechanics for quantum mechanical systems, and so on. One of the features that physical theories have is that they allow us to assign properties to the models. So this property assignment map or function is just a formal way of representing what the different models or possibilities indeed represent. So for instance, you might have a Boolean property, a property that can be true or false, that you would represent as a map from the space of models to a two-element space consisting of the false element and the true element. So for instance, the property might be, is the total mass of all of the objects in the system equal to 1 kilogram? If it is, then this map would map that particular model representing that state of affairs to true, and it would map it to false otherwise. We can also do it for real valued properties as well, right? So in this particular case, it might map the total mass of the system of the objects described to a real number that represents their total mass. And we can do that for all sorts of properties. So one of the things that's going to be important is that there's going to be one property assignment that picks out amongst the kinematically possible models, the nomologically possible ones. These are the ones that satisfy the laws of a theory of interest. So what I have in mind here is I have in mind some very large space of possibilities and some slightly smaller space that satisfy all of the constraints on the kinematical quantities that the theory posits. So for instance, we might have a theory about electromagnetic phenomena that requires that there be a strict connection between electric fields, magnetic fields, and their changes over time. These are, of course, traditionally given by the Maxwell equations. So we might have kinematically possible models that involve all sorts of random assignments of electric and magnetic fields, but only the assignments of electric and magnetic fields that satisfy the Maxwell equations are going to be the nomologically possible ones. So amongst that space of models, this Boolean property assignment, which I'll call L, assigns true to the ones that are nomologically possible, the ones that satisfy the equations of motion, and false to all the others. Some properties we're just going to suppose are observable properties. I want to emphasize that which ones those is not merely a formal matter. What I mean by that is that the mathematics don't identify which properties are observable, which are not. That's an interpretive matter for the theory. So, but once that information has been provided, right, we can define in particular an equivalence relation on the codomain of O. Remember, the codomain of O are just the values that the property assignment assigns to models. And this equivalence relation is a relation of mutual observational indistinguishability. So two values for the property assignment are mutually observationally indistinguishable when there's no way that we can tell the difference between the two. In most situations, this equivalence relation is going to be pretty trivial. The reason why I introduce it is that there are some situations involving gauge theories where we do want to have different property assignments made to different models that are nonetheless indistinguishable from one another. What's really important, though, is that we can use this relation for each of the observable property assignments to define when two models are mutually observationally indistinguishable. So we can say that two models are mutually observationally indistinguishable, S and S prime, just when for all the observable properties, the property assignment to the first one is observationally indistinguishable from the property assignment made to the second one. So I don't take this to be a particularly controversial way to go, but these ideas are going to play a role in my formalization of the surplus structure argument. So now let's talk about transformations. These are going to be the underlying mathematical things that are going to define symmetries. Transformations I'm going to define as bijections on the space of kinematically possible models. And I'm going to assume that the transformations are not automorphisms of the space. The reason for this is that I want to exclude from consideration maps that we already believe take models to mathematically equivalent models. Now, some transformations, some bijections of this sort are going to preserve properties, relations, or other structures on the space of possibilities. So suppose let's consider one simple case where we are interested in properties. Some property X represented by an assignment, a property value assignment X. We can say that the transformation preserves this assignment just in case for all of the models in S, the property value that gets assigned to S is the same as the one that gets assigned to S after transforming it with T. So preservation of property assignment is exactly what it sounds like. Some model has a property. The transformed model also has that property for all models. That's what it means for a transformation to preserve a property assignment. Okay, so we've got a notion of a symmetry that preserves a particular property. We've got notions of equivalence. we can combine the preservation property with the observational properties to describe in particular observational symmetries. So we can say that a transformation preserves observational properties just when for all the models, any particular model is observationally equivalent to the transformed model. So the idea here is that even though a transformation may map models to non-identical models or models that are not mathematically equivalent, if the transformation is an observational symmetry, then it will only map any model to another model that's observationally equivalent to it. I want to know that this is stronger than just preserving the relation of mutual observational indistinguishability, because it requires that any observable property is equal to the observable property composed with the transformation for all observable properties. So it's a bit stronger than just preserving mutual observational indistinguishability. That's important because it's possible to preserve mutual observational distinguishability while mapping via T models to other models that are not physically equivalent in any relevant sense. I can give you examples of this if you'd like in the question and answer period. Okay, so now that we've got this basic formal structure set up, we can actually describe what I take the form of the surplus structure argument to be. So we start once again with the space of kinematically possible models. And once again, we let L be the Boolean property assignment, the nomological possibility. So the first step is we consider some property assignment X and some transformation T. And then we suppose that T is both an observational symmetry and an L symmetry. That is to say, it preserves being a solution to the laws of the theory. But we also suppose that it's not an X symmetry. So it doesn't preserve the property labeled by X. So we can conclude from that that X represents a property that is not observationally detectable. For if it were observationally detectable, then T would not be an observational symmetry. So the conclusion is, ceteris paribus, we should prefer an interpretation of the models that dispenses with the reality of the property, or dispenses with the property formally over one that does not. There's a few features of this conclusion that I would like to highlight. One is that there are two versions here.
15 minutes, I'm sorry.
Great, thank you very much. There's two related norms in play, and both of them are Occamist norms, norms for a preference for simplicity. One is ontological and one is representational. So the ontological one is one where we dispense with the reality of the property assignment. We may keep it formally for convenience, but we don't think that it represents anything real. And then another is representational, where we dispense with the property assignment X altogether in the space of models. I would also like to highlight that this is ceteris paribus because there may be defeating reasons why, even though this holds, we still hold on to the interpretation that does not dispense with X or with the reality of X. So why is that? So one is that the Occamist norms for simplicity are just one of the many norms we have for selecting which theories we prefer. For instance, we may not have a suitable alternative. You'll remember in the case of the Leibniz-Clark correspondence, one of the reasons why the Newtonians did not reject absolute space, despite Leibniz's arguments, is that they had no alternative structure with which to formulate the equations of motion necessary for Newtonian physics. If we reject absolute space, then there are problems describing Newtonian physics. The mathematics available for doing that wouldn't be available for some hundreds of years. Another reason is that the relations that we want to hold between different theories, such as embedding of one theory of another and the unity of interpretation of our different theories, bear on which structures we should reify. So it might be that we want to reject, we might be inclined to reject the reality of a particular property or feature on its own, but when in combination with other theories, we have reason to keep it. There's a circularity objection that's sometimes made. We can find this in the work of Shamik Dasgupta. It has to do with the fact that a surplus structure argument presupposes a list of observational properties, yet he says we often use premises about symmetries in order to work out which physical features fix the observational data. So we can't define symmetries to be those properties, in this case, observational symmetries, to be those operations that preserve features of the observational data. But I think that this presupposes a kind of foundationalist epistemology to this whole business. I think that what matters is rather the coherence of an interpretation with symmetry. So I think that what we can do in practice is we employ a sort of reflective equilibrium. We propose first plausible and empirically adequate theory with models for a system of interest with plausible observable properties and representation relations. Then we identify the observable symmetries. Then we test the models, the observable properties and representation relations. That can be by experimentation, by theoretical work, and it can be too wide or too narrow. I'll skip over some of these reasons in the interest of time, just to finish off the reflective equilibrium argument here. So in the process of doing so, we may identify surplus structure through the sort of surplus structure argument that I've described. That can lead us to reduce states by identifying states related by an observational symmetry. It can also allow us to change the mathematics we're using by changing some observational symmetries to isomorphisms. That's a typo here. That should be isomorphisms. And which one we choose depends on balancing the interpretive or explanatory considerations at hand. So after this process, we can then return back to the original step and go again. So contra bellit, neither of his two principles, I think, play actually a role in the surplus structure argument. Instead of his definition of symmetries, I think that symmetries are defined more or less formally. Symmetries of laws are just one type. And instead of his principle D2 as formalizing the underlying principle that's used in the surplus structure argument, I've given it a different form, a form that I think only makes a ceteris paribus connection between symmetries of laws, observational symmetries, and equivalence that's implemented via a procedure of reflective equilibrium. Thanks for your patient attention.
Thank you, Sam. So we have around 5 minutes for questions. You can raise your hands, write down that you want to ask a question in the chat as well. Christian, please.
Okay, thank you so much for your presentation. More than a question, it's a clarificatory point.
Yeah.
And I think I missed it because you went through that stuff over your presentation. What's implied in your use of the expression surplus? Is it because it's redundant, dispensable? That wasn't that clear to me.
Right.
Thank you.
Let me go back here. So the sense in which it's surplus is that the conclusion of the argument is that we should prefer an interpretation of the models or the theory that either dispenses with the property in question or dispenses with the reality of it. So the sense in which it's surplus is comparative or relational. A property assignment represented by X is surplus in this sense when there is another interpretation of a theory that dispenses with the reality of that property assignment that is reified in the first, or dispenses even formally with the property assignment in the first. So on this, this argument allows us to identify properties that are not observationally detectable. Whether they're surplus then depends on the availability of an alternative theory that we can select that dispenses with that property. So in that sense, being surplus is only a kind of a relational feature between one theory and another theory that are very similar, except one rejects or dispenses with a property assignment or the reality of a property assignment. Does that help?
Yeah, definitely, definitely. I was trying to figure out if it was the same use that Redhead, has in his articles from the 70s. Yeah. Yeah. Thanks.
Yeah, you're welcome. Maybe I can, oh, sorry. I was just going to say, like, a nice illustration of this sort of idea comes in gauge theories, like in electromagnetism, where we have a gauge potential that we can change and the physics stays the same. In that case, it's so helpful to have the gauge potential around that we don't always dispense with it technically. It still shows up as a mathematical object in the theory, but we dispense with the reality with it. We don't think that a particular value of a gauge potential represents anything real.
Okay, thank you.
Thank you, Christian. Do we have time for one more question, I think? Oh, okay. Let me make just one, just a remark as a follow-up to what you just mentioned as an example, Sam, the case of this potential in electrodynamics in quantum cases, like in the Hadronov-Bohm effect. If we got rid of it beforehand, for example, or then we wouldn't have the mathematical means to satisfactorily explain that case. So I think it makes a lot of sense when you say that the surplus structure argument only runs in relational context, and it's not a sort of in isolation thing that you could decide. I think that's a nice example.
Yeah, I agree with you completely about that. I think there in the Aharonov-Bohm case, the relations between theories are really important in deciding what we should dispense with. In this particular case, it's a relation between classical electromagnetism and semi-classical electromagnetism, where the interpretation of the theory we may want to have a unified interpretation of electromagnetism in different contexts. And the fact that some of the properties or structures that electromagnetism uses may have different roles in the two cases may mean that even though we think that, oh, we should totally throw away the potential in one case, in the other, we think actually in this new context, in order to understand the relation between classical and semi-classical electromagnetism and have a unified interpretation of them, that we should reconsider that original inclination that we had. So that's exactly my view.
But sorry, but do you see in any non-relational case in which you have a single theory, and then in that theory you identify a bit of a surplus structure in one theory without a comparison to another theory?
So I think that the first two steps of the argument allow us to select properties that are not observationally detectable. But then what we do after we identify such a property depends on the theoretical resources we have available to us. So I think that, for example, in the case of Newtonian space-time, the existence of absolute space was acknowledged by Newton as not being observationally detectable. Newton acknowledged that we will never be in a position to know the absolute positions or the absolute velocities of things, but he didn't have an alternative that would provide a suitable foundation for mechanics. It was only through the development of mathematics that we came to what VII called Galilean space-time. Wasn't Galileo who first described the mathematics of that, but it was VII who called it Galilean space-time. That we finally had the mathematics to be able to dispense with absolute space and provide a foundation for Newtonian mechanics that did that. So I think that we can identify properties that are not observationally detectable, and this may provide an incentive for the development of theories of physics to try to find new structures that dispense with them. But if we don't have an alternative that we can turn to, then it's often better for us to keep the imperfect theory that we already have.
Thank you, Sam. It's time to move on. Now it's our third and last speaker of this session, Christian Laroulette, from the University of Cambridge. I'm sorry, I forgot to mention Sam's affiliation too. Sam is from the University of Minnesota and also affiliated to the Munich Center, right? And now Christian Laroulette is affiliated to the University of Cambridge. Sorry about that.
Hello.
Go ahead.
Cambridge has a pretty bad internet, so I hope it runs smoothly while I'm talking. Thanks for the organizers. I'll speak in English here. So the guiding motivation for this talk and for the dissertation I'm currently writing is the controversy we see about the quantitative status of measurements in the human sciences. It is common for researchers in economics, psychology, and medicine to use measurement scales that are not obviously quantitative. Think of scales of happiness, empowerment, depression, among many others. And researchers use these scales in ways that are methodologically controversial. In particular, they take averages of the data gathered with these scales to, for example, compare happiness or depression, etc., among those exposed to a treatment with those in the control group, in order to make causal inferences. But standard measurement methodology prohibits such comparisons when the scales are not strictly quantitative. And so we get harsh responses by methodologists in all these disciplines. So in short, we see much tension between methodology and research practice when it comes to inferences from measurement results. My main thesis is that standard measurement methodology can be too much of a straitjacket. And for articulating this thesis, I characterize measurement scales epistemically, that is, in terms of researchers' beliefs. This is developing ideas from work that is forthcoming in philosophy of science. In this paper, I focus on rejecting the prohibition for making inferences with averages coming from ordinal scales. This is a general prohibition that applies to all ordinal scales. I start by reviewing the standard justification for the prohibition, showing that it can only vindicate a qualified prohibition, but then challenging even this qualified version, and I close addressing objections. So the intuitive idea behind an ordinal scale is that it informs only of order. It doesn't inform of the distances between the elements order. So if our measure of happiness is the answers to the question of how happy you are, and these answers come in 3 categories, saying that this scale is ordinal is saying that we don't know the sizes of the intervals. That is, we don't know if the distance between the first and the second level is the same as that between the second and the third level. The contrast here is that in quantitative scales, we know that all the intervals are of equal size. Say all the marks in this ruler are 1 centimeter apart. So in standard methodology, this is formalized by defining ordinal scales as those for which all order-preserving transformations of the data are admissible. So we can use 1, 2, 3 for coding the happiness data, but we could also use 1, 6, 8 or 2, 5, 25. The idea is that all these numerical assignments are equally acceptable because they all preserve the order. Now, the argument for the prohibition turns on 2 premises. It starts with the set of admissible transformations that define ordinal scales, all the order-preserving ones. And then it states the following invariance principle, that when inferring claims from measurement results, only the conclusions that remain true under all admissible transformations are validly inferred. Now, because the computed averages of measurement data change dramatically when different order preserving transformations are applied, the conclusion typically drawn is that we shouldn't make inferences with averages from ordinal scales. So for example, if we measure the hardness of two groups of minerals with Mohs scale, which is an ordinal scale that goes from 1 to 10, and we compute the average hardness, although here group A has a higher average than B, we should not infer that A is harder than B on average, since applying this permissible transformation, as well as many, many others, makes it that B's average is higher. So this is the argument for the prohibition. Now, it is common to see the prohibition stated in an unqualified way, as in inferences about group averages with ordinal scales are never valid. But the argument we just saw cannot justify this unqualified prohibition, simply because the argument includes an invariance clause. Whenever the conclusion is invariant, all the admissible transformations, the argument doesn't prevent the inference. Now, let me state a condition for when this happens for relative average comparisons. So here are two groups of people, the blue and the red, which are the richest and the poorest group in this table taken from a famous paper by Easterlin. They are measured in a happiness scale with 3 levels. There's a mathematical result that says that if the cumulative distributions of one group first order stochastically dominates the other, then the computed average of the first will be higher than that of the second, no matter which order preserving transformation is used. So whenever this condition called first order stochastic dominance holds, even by the lights of the argument for the prohibition we just saw, we can compare groups' averages with ordinal scales. In this real world example, stochastic dominance does hold. This graph shows the cumulative distributions. The key is that they don't cut across. No? So the cumulative of the blue group lies on or below that of the red group everywhere, and strictly below over at least one interval. So this is what stochastic dominance requires. So the intuitive explanation is that in all the happiness categories, except for the highest, we see that there's more red people than blue. So no matter how big or small are the distances between the levels of happiness, that is, the relative sizes of the intervals of the scale, which is what we are varying when we apply transformations, the blues remain on average happier than reds. So to sum up, when the evidence is strong enough such that stochastic dominance holds, the standard argument against inferences from ordinal scales doesn't prevent these average group comparisons. The argument only vindicates a qualified prohibition that includes the invariance clause. But I think even this qualified prohibition is not sound. In this talk, I present the argument with a simple case, avoiding the formalisms, but I'm happy to share the written paper for those interested. So imagine that a researcher wants to compare the hardness of two groups of minerals, A and B, each containing 4 minerals, so as to confirm or disconfirm hypothesis H, that A is on average harder than B. Using Mohs scale, she obtains these measurement results. Had the scale be quantitative, our researcher would have inferred H, no, just deduce H, since A's average hardness 3.5 is larger than B's. But Mohs is the paradigm of an ordinal scale, so the prohibition says this data cannot bear on hypothesis H. Moreover, this figure shows that the cumulative distributions cut across, so stochastic dominance doesn't hold. But let's ask, what must our researcher rationally believe about the intervals of the Mohs scale, that is, about the distance between the different levels, to be justified in using this data to confirm H? The standard view, which I'm criticizing here, will say, well, she needs to believe her scale to be quantitative, that is, that all the intervals are equal, so that the distance between a 1 and a 2 in the figure should be the same as the distance between a 2 and a 3, and so on. But what is the inferential relevance of this belief? Why does it enable the comparison? Because we know the relative sizes of the intervals, and thus the width of the areas here, we are able to compare the areas where the cumulative of A is above that of B, with areas where the opposite is true, so that we can infer which group is harder than another. But then what matters is to be able to compare these areas. No? This is what enables the inference. But for this, we don't need to be certain that all intervals are of exactly equal size. In this particular example, say the interval from 2 to 3 is irrelevant for this comparison. We just need to know the relative size of the intervals where the groups differ. So in this example, because we have 2 minerals in each group with the same degree of hardness, to conclude that set A is harder than B, we just need to know that the hardness of a 1 and of an 8 in the Mohs scale taken together are harder than a 2 and a 3 taken together. In other words, A is harder than B if and only if the degree to which a 2 is harder than a 1 is less than the degree to which an 8 is harder than a 3. Put it yet differently, what a researcher must rationally believe in order to deduce H is only that the size of the 1 to 2 interval is less than 5 times larger, the average size of the intervals 3 to 4, 4 to 5, and so on until 7 to 8. The key is that this is a different and much weaker claim than that all intervals are exactly of equal size. So perhaps the evidence doesn't warrant this weaker belief. Perhaps it does. But the conceptual point here is that the belief of having a quantitative scale is not needed for deducing H. This is why the prohibition should be rejected. We can make sound inferences about relative averages with non-quantitative scales. That is, with scales that for which we are not certain that all the intervals are of equal size. Now, before addressing objections, I want to stress a bit more the problematic nature of the epistemology that grounds the prohibition. So first, the argument for the prohibition that we saw tacitly assumes that measurement inferences are restricted to deductive inferences. Of course, even restricting ourselves to deductive inferences, we already challenged the prohibition. No? But why restrict only to deductive inferences? If we analyze this inferential problem of average comparisons in Bayesian probabilistic terms, as I do in the paper, we can show that what takes data to bear on hypotheses of average comparisons is even weaker than what I've mentioned so far. So our confidence in the relative sizes of the intervals can be more nuanced, less certain, and still get data to bear on average comparisons hypotheses. And this is missed by the epistemology assuming the prohibition's argument that reduces itself only to deductive inferences. But second, and more importantly, I think, clearly not all average comparisons with ordinal scales where stochastic dominance doesn't hold are epistemically on a par. In our example, imagine the fourth element of group A has a hardness of 10 instead of 8. Surely we would know now that A is harder than before, no? And so that it is in a better position than before to have a higher average of hardness than B. And the converse is true if the fourth element is of hardness 4 instead of 8. But these variations are not captured in an epistemology that says we can only confirm H if we have a quantitative scale. Otherwise, we cannot say anything. So in the paper, I expand on this issue, showing that sticking to the prohibition leads to, or can lead to, probabilistic incoherence. So summing up, we don't need to believe our scales are quantitative in order to make justified average comparisons. Even if stochastic dominance doesn't hold, there are beliefs weaker than having a scale with equal intervals, but are still sufficient for making group comparisons. So the qualified prohibition should be rejected on principled grounds. So I anticipate two kinds of objections, semantic and epistemic. The semantic objection questions the meaningfulness of talking about intervals and averages of scales widely considered ordinal. For scales such as happiness scales or hardness scales or depression scales, it makes no sense to speak of averages, some people would say. Though popular, I don't find this idea compelling. I think on the face of it, phrases like the pandemic affected much more his happiness than hers don't look like meaningless, and of course they are commonly used now. I think behind this objection lies the claim that we speak meaningfully about averages and intervals only when we are talking about quantities. And these ordinal scales don't measure quantities, since happiness, intelligence, hardness, depression are not quantities. The problem here is that nobody has shown these attributes are not quantities. And it's not clear how can someone actually show this negative claim, since even the positive claim that something is quantitative is not straightforward to establish for unobserved latent attributes. This has been, I think, shown very persuasively by David Sherry for the case of temperature, where its status as a quantity that we are successfully quantitatively measuring ends up being justified by quite complex coherentist and pragmatic considerations, not by, say, straightforward verification of Holder's axioms for quantitativeness. So the lack of success in developing quantitative scales for social sign attributes cannot be taken to strongly support on its own, at least, the negative claim that these are not quantities. In the end, as Sherry argues, scientists' consideration of an attribute as quantitative, I think it's better understood as a working hypothesis, one that, of course, might end up being rejected by theoretical and or empirical considerations, but only after much effort has been put into it, surely not by lack of imagination or positivist qualms. No. So I take it that this semantic strategy cannot vindicate at least a general prohibition, no? A prohibition for all ordinal scales. I think other objections that are serious are epistemic. Here, the objector grants what I've said about the validity of inferences, namely that if my imagined researcher holds rational beliefs about intervals differences, she may deductively infer the hypothesis about relative averages. But no, the claim would be that nobody can have such beliefs, since we just don't know how the different intervals compare. Now, I think we can distinguish between two versions here of the objection. First, the more ambitious skeptic claim that researchers just cannot hold rational beliefs about the intervals differences in the attributes of interest, like happiness, depression, etc., because there's no evidence that can justify such beliefs. Now, why would this be the case for all the attributes of interest? Remember, I'm targeting the general prohibition. It cannot be that all these attributes are not quantities for the reasons I just gave. A more plausible line is the idea that whenever we are able to form rational beliefs about intervals differences, it is because we are also able to go all the way and construct a quantitative scale. So in other words, we never find ourselves with an ordinal scale and with rational beliefs about intervals differences. Now, arguably, I think the predominance of the representational theory of measurement, especially when it is seen erroneously on my mind, as providing an account of how measurement goes in practice, makes this idea more plausible than I think it is. In that framework, either one is able to establish a quantitative scale or one is not able to do so, but have only established an ordinal scale. There are no scales in between there, but that's because there are no axiomatizations in between. But this doesn't
15 minutes, Christian, I'm sorry to interrupt.
But this doesn't speak to researchers' actual epistemic situation, that is to their confidence in their measurements and the inferences they afford. From an epistemic perspective, this argument is assuming a dichotomy between, on the one hand, knowing nothing about interval differences, and on the other, knowing everything, so that we are able to construct a quantitative scale. But this, I take it, is an implausible description of the situation of all researchers at all stages of measurement development. If well-established quantitative measurement is a hard-won achievement, as scholars like Hasok Chang and Aaron Tal have shown for temperature and time, respectively, then there's plenty of space for being on the way to it without being already there. Now, a second version of the epistemic objection is more modest. It grants that researchers may hold rational beliefs about intervals differences, but since ordinal scales are defined as those that inform of rank order only, then by definition, the beliefs about interval differences cannot be based on such scales. So in this view, the prohibition survives if it is understood more narrowly, as prohibiting making inferences from averages when all the information we have comes from the ordinal scale. Again, I think this objection betrays the predominance of RTM. The objection is surely correct that to complain that the very definition of an ordinal scale in standard measurement methodology says that it encodes only information about order. But the problem here is that there's a substantial gap, I think, between that definition on the one hand and the actual scales developed by researchers out of background knowledge and that are widely considered ordinal just because they are not quantitative, on the other hand. Once we look at the concrete examples of ordinal scales given by RTM scholars, scales for hardness, air quality, wind force, it's hard to reject the claim that they inform more than order, despite not being quantitative. In the paper, I discuss Moss' scale of hardness in some detail, arguing that it is more informative than order, and that Moss himself developed it with that intention. But I think this arguably generalizes to other cases. As Adelson and Tuggy put it long ago, the typical state of knowledge, short of metric information, is not rank order information only. Ordinarily, one possesses something more than rank order information. So the response to the second epistemic objection boils down to granting that the qualified prohibition can be saved for ordinal scales strictly defined, but not in general for actual scales considered ordinal. And since the point is to reject the actual prohibition, the one that matters for practice, I take that this is no concession. So to finish up, the qualified but still general prohibition should be rejected. This is because beliefs needed for making average comparisons are less demanding. Now, to be clear, I'm not saying that all ordinal scales are enabled to give us these comparisons. Surely there are some for which we have very little evidence of intervals differences. But the claim is that this need not be true of all cases. No? And that's why the general prohibition should be rejected. And the key lesson, I think, is that the category of scales considered ordinal isn't homogeneous. Ordinal scales need not be all on a par with regard to how informative beyond order they are. So making inferences from averages needs a case-by-case justification. And then the takeaway is that neither a general prohibition nor anything goes are defensible positions. Thanks very much.
Thank you, Christian. Sorry. So we have around 7 minutes, something like that, for questions. Sam?
Thanks, Christian. I think this is the second version of the talk that I've seen. One question that I had was, I like this version. So I'm really glad to see how your project is progressing. So my question has to do with in situations where you think that there is some justification for making these sorts of inferences, whether it's whether it's the best way to describe it as making inferences about averages. So like in the case that you mentioned where even setting aside researchers' underlying beliefs about maybe some true underlying quantitative scale for the measurement, that whenever we have stochastic dominance, we can still make comparisons of one set or group of data dominating another. We can describe, if we assign numerical labels to the data and take averages, then the comparison of the numbers gives a representation of the dominance. I wonder though, like, should it really be described in that case in general as a comparison of averages? Because I can imagine someone thinking, and this is very much dovetails with your conclusion, thinking that the researcher thinks, actually, I don't think this is a quantitative scale anyway, but I can still make this comparison because of these technical results about one set of data stochastically dominating another. And they might say, oh, this doesn't mean that the average of one is more than the other. It has some more kind of qualitative notion of being larger than, right? The reason why I'm mentioning this is that when you suggest like comparison of averages, if one is not being careful, one might slide accidentally into saying things like, oh, well, the difference between these two averages is larger than the difference between those two averages, or and reifying some information about the exact value of the quantity. And I wonder if in these cases, adopting a different terminology, not saying that the average is larger than one, would be a better way in some cases to describe what the underlying beliefs are. Maybe to put the question to you in a word, do you think that this variability of belief should correspond to a variability in terminology that researchers use when they talk about these group comparisons?
Thanks, Samuel, and thanks for staying to listen for the second time talk. I think it's a really nice point. And because in a way, my project is always having in mind that, you know, psychologist or that sociologist or economist that is trying to make quantitative research about an attribute, knowing that the measurement that he or she has is not, doesn't afford confidence in the distance of the equal distance of the intervals. No? And you're setting forth the case for the researcher that is sort of agnostic or doesn't want to commit to the quantitative nature of the attribute. And I take it that in that case, that I'm sort of not speaking to that case, no? But in that case, then it would be advisable for the researcher, yes, to avoid average talk, no? Because they don't need it and they want to remain neutral about the status of the attribute, no? So definitely. And I guess there should be a qualitative way of saying this group is, but I think it's tricky though, no? Because I think it's natural, the argument, the interpretation that I'm giving, you know, is an epistemic one. It's saying, well, we don't know what the sizes of the intervals are, you know, but the point of the stochastic dominance is whatever they are, one group is going to be on average harder than the other one. I guess I'll need to think more about what the person who even thinks that the attribute is not quantitative wants to frame, you know, use as a frame for making that comparison. You know, one group is what than another, no? But because the point is not talking about the median, for example, no? Then you don't need that result for talking about the median. I guess it's an interesting thing. And I think it's a very much underexplored work, which is, even in the metaphysics literature, there's a lot of talk about what is, metaphysically speaking, a quantity. And I think there's not much work on what is, metaphysically speaking, an ordinal attribute, you know, an attribute for which it's not that we don't know the interval sizes, but we couldn't know. And I think that sort of would bear on the correct description of the case you are giving. Thanks for the question.
Thanks. We have time for one more question, I think. Christian?
Gracias, Pablo. Thank you so much, Christian, for your presentation. I wanted to take you back to the representational theory of measurement. It seemed to me that it was more philosophically loaded. And I couldn't quite get what was the model you draw from it. Didn't it work for the purposes of your argument? Why was it left, you know, aside? The representational theory of measurement.
So, yeah. So in that framework, there's no scales between ordinal and interval. Or quantitative, you know, lumping interval and ratio scales. In fact, in that framework, there could not be any scale. There are theorems proving that there could not be any scale in between ordinal and interval. And what I'm saying is that might speak to the metaphysics, you know, of the world, that they just might not be possible scales in between, but that doesn't speak to the epistemic situation of the researchers, you know. So if you have any knowledge about how objects compare, that is not quantitative, no? So you cannot say this is twice as large, you know, or change large for the pertinent predicate than this other one. But you know something more than just that one is higher, larger than the other one. That situation you can understand it epistemically, no? But you cannot understand it in terms of the resources that the representational theory of measurement provides. No? And that's why I'm sort of using a Bayesian framework, and the paper that is coming in Philosophy of Science is sort of motivating this need for not limiting ourselves to the representational theory of measurement. I hope this helps.
Thank you. Yeah, thanks.
Yeah, thank you, everybody. I think our time is over. So thank you, everybody, for coming up, for showing up, for the interest in these 3 nice talks. to the people in the organization. It was great to see you all. So have a good day, everybody.
Yeah, thanks to the organizer.